SwayamPrabha.
Welcome. So in the last class we have seen what is parameterized algorithm, what is an FPT algorithm, and we have seen easy 2 to the power k time algorithm for finding a minimum vertex cover, and now we are designing a faster algorithm for minimum vertex cover. So let's continue. So faster FPT algorithm for vertex cover. Okay, and for that we have used we will use that observation. So what is the observation? That if the maximum degree of the graph is at most 2, minimum vertex cover can be computed in polynomial time. Okay, now what is the algorithm? First of all, again it's a recursive algorithm, again it's a search tree based algorithm. The base case is if the maximum degree of the graph is at most 2, then return then compute a minimum vertex cover in polynomial time and return it. Return yes. So let's talk about decision version. Return yes if its size is at most k. It means we are given a graph G and an integer k, and the question is what is the size of the minimum vertex cover at most k or not. Okay. So next, otherwise the minimum degree. So within comment, otherwise the maximum degree of the graph is at least 3. So pick such a vertex. So let U be such a vertex. Of course, we will have those sanity checks. If k is 0 and there is an uncovered, there is an edge in G, then return false. Else if k is 0 and else if not k is 0, if the graph does not have any edge, then return true. Else what you do is that let U be such a vertex. Either you pick U and recurse, but if you don't pick U, you have to pick its neighborhood of U. So return, in this case, return, call the vertex cover problem, this function recursively, and you remove U and drop the budget by 1 to make it k is less than equal to 0, or either after picking U and you deleting U, in the remaining vertex there is a vertex cover of size k minus 1, or look for is there a vertex cover of size. If you don't pick U, you need to pick the neighbor of U. NU is the set of vertices which has direct edge with U. In this case, drop the budget by NU. Okay, so this you return. So what is NU? NU is set of vertices such that there is an edge from V. Okay, so this is the algorithm. So let's analyze it. So pictorially, let's see G and K. Now in one branch it picks, suppose U is that vertex, so G comma K minus 1, and in the other branch it is G and you pick the neighborhood in U and K minus cardinality in U, which is like, you know, there is some graph G prime and K prime, and K prime is NU is at least 3 because the degree of U is at least 3. So K prime is less than equal to K minus 3 and so on. Now here also the height is K, but one branch is much more shallower. So how many nodes are there? So let's see. So let T n comma K be the maximum number of nodes in the search tree of the above algorithm on any graph with n vertices where we are looking for a vertex cover of size at most k. Okay, so T in k then is less than equal to T in minus 1 k minus 1 plus T in minus 3 k minus 3, and of course T in 0 is 1. This is for all n. Now, because n and k are dropping by the same quantity, so this recursion tree will at the leaf k will be hit at 0. So, it is enough. So, define T prime of k is to focus on k because it will be a function of k only, T in k. The max of n in n T in k. Now, then what is T prime of k? T prime of k minus 1 plus T prime of k minus 3, and the base case is T prime of 0 is 1. Okay. Now, we need to solve this recursion. Now, there is a standard technique to solve this recursion. So, for that we will solve this, we will guess the recursive solution. So, let T prime k be less than equal to there is a form of T prime k with this sort of recursions. It is c times lambda to the power k for some constant c and lambda. Now, let us put it here. This is c times lambda to the power k. We need this to be less than equal to, for this to hold, it is enough to have c times lambda to the power k if it is less than equal to c times lambda to the power k minus 1 plus c times lambda to the power k minus 3. If this is true, then this inequality holds. Okay, because then t prime k minus 1 will be less than c times lambda to the k minus 1, and t prime of k minus 3 will be c times lambda to the k minus 3, and if this sum is more than c times lambda to the power k, or at least as high as c times lambda to the power k, then this will be greater than equal to t prime of k. Now this is if and only if lambda cube minus lambda minus 1, this is less than equal to 0. So solving this, what we get is lambda is and of course lambda c and lambda must be positive, and c must be positive and lambda should be greater than 1. So with all these constraints, what we have is lambda is, we need to choose lambda to be equal to, for lambda equal to 1.4656, the above inequality holds. Hence, the number of nodes in the search tree of the above algorithm is at most 1.4656 to the power k, 1.4656 to the power k. Sorry, this will be greater. This should be greater than, enough to have this. Okay. Now the computation at every node of the search tree Now, what is the computation? So, let us go to the algorithm. So, at the base case, maybe we need to find a minimum vertex cover for a collection of cycles and paths, a disjoint collection of cycles and paths, and the rest of the computation is takes order n time. So, the computation at every node of the search tree takes order n time. Even for the base case, when the max degree is at most 2, finding the minimum vertex cover takes order of n plus m time. You simply needs to iterate over all the edges, and but the number of edges is at most 2 times the number of vertices, because the degree is at most 2. It's basically like the same number of vertices, because sum of degree is twice the number of edges. So the number of edges is at most the number of vertices in that case. So n order of n plus m is order of n only. So computation at every node such that takes order n time. Hence the runtime of the algorithm is big O of 1.4656 to the power k times n. Okay, good. So in general, how to solve recurrent solutions of the form, say Tk equal to T k minus d1 plus T k minus d2 and so on. It's like you guess, let D be max of d1 to dp, and you guess Tk is less than equal to C times lambda to the k. The value of C we will get from the base case of this recursion. So this boils down to it lambda to the power k is greater than equal to lambda to the power k minus d1 plus lambda to the power k minus d2 lambda to the power k minus dp, which is if and only if lambda to the power d minus lambda to the power d minus d1 plus minus lambda to the power d minus dp, this is greater than equal to 0. Okay. So next what we will see is what is called a kernelization. So often in real world instances or in real life we do some pre-processing before applying the algorithm to solve the problem. So we often execute some efficient pre-processing techniques or pre-processing algorithms on the input instance before running the main algorithm to solve the problem. Kernelization formalizes such pre-processing techniques. Okay. For example, for vertex cover, we can simply delete all the isolated vertices. The input instance can contain some isolated vertices, and you can simply delete it without affecting the optimal solution. Or there are some more of this sort of preprocessing techniques which can sort of clean the input instance and focus on the core problem. For example, for vertex cover, all the degree 1 vertices we can delete and take its neighbor as in the part of optimal vertex cover. So, these sort of simple techniques we can use to clean up the data to do the pre-processing. So, what is kernelization task? So, a kernelization algorithm takes a parameterized problem instance as input and outputs an equivalent instance of bounded size. What do I mean by that? So, suppose there is an instance x comma k is the parameter, and the parameterized algorithm takes x comma k, this is the algorithm A, and outputs an equivalent instance. That means this new instance, the output instance is a ES instance if and only if the input instance is a ES instance, and the size is bounded by some parameter, by some function of parameter alone. So, size of x prime is less than equal to g of k, and k prime is also less than equal to f of k for some computable functions f and g. So, in the next class we will see some examples of parameterized algorithms for vertex cover and some other problems, and then we will see that this kernelization algorithm is really the other side of the parameterized algorithm and its connection to FPT algorithms. Okay, so let us stop here for today.